lot of research has been conducted on the relationship between things on our computer screens and natural language. For example, in the domains of image synthesis and image captioning, it is possible to take a prompt like an astronaut riding on a horse in a photorealistic style and obtain an image like this using state-of-the-art methods. Then, even though this is a really weird image that is probably not found in any training dataset, a state-of-the-art image captioning system is able to describe this image accurately: an astronaut riding a horse in space. So while not perfect, those systems work really well, but not all of what that we do on our screens are 2D illustrations. In fact, this being a computer graphics conference, we care a lot more about 3D worlds than just 2D projections of them or 2D illustrations. So how does it look in the 3D world domain? Well, there's been some research on turning natural language prompts into 3D scenes. However, there has been barely any search on the opposite, like turning a 3D scene like this into a text that, for example, an actor in the world could describe the scene around them, or that if we could make our 3D worlds more accessible to people who are visually impaired. So, as a first foray into trying to describe scenes with text, we would like to introduce a procedural content generation system that synthesizes 3D scenes with automated generation of textual descriptions for them. Our goal is to generate fantasy scenes with accurate textual descriptions in a proof of concept system. So first I'll introduce you to the method we use to generate those scenes and accompanying textual descriptions, and then we'll evaluate the results with a user study and discuss them. So, the core of our system is a scene relationship graph. As you all know, in scene relationship graphs, usually the nodes represent the objects and the edges the relationships between them. So, in order to obtain a scene relationship graph procedurally, we utilize probabilistic graph grammars, which are a nice user-definable way of generating a wide variety of random graphs using production rules. And then, because we want a scene and a text that correspond to each other, the simple thing we do, we generate first a scene out of this graph and then a text of this graph. And if we do our job well, of course, they'll belong to each other. So the way we go about generating a scene is pretty simple. We construct a scene evaluation function and then use the in scene layout synthesis popular Markov chain Monte Carlo optimization method. To construct this evaluation function, we build an energy function that describes all the spatial relationship factors within the graph and some implicit constraints, for example, that objects should not clip into each other and pathways should be of a certain shape that does not collide with objects, not collide with other pathways, and have not too steep turns in the pathways. So, maybe as an example, I'll quickly go through how a single spatial relationship is turned into a function. The way we do this is to first think up of some logical constraints that quite well describe this relationship. For example, the sack of flour to the right of the windmill building will be described by a certain distance boundary where, like, we say they are close enough to each other, so the distance between them is less than 2 in this example. And the to right of is then described by looking, where's the front of the windmill? Take this vector and then calculate the angle between this vector and the vector between the two objects and check whether this corresponds to the right side of the windmill, so an angle of 0 to the right side as seen from the windmill. Well, I'm looking onto the windmill from the front. So now we have two logical constraints, which are obviously not quite a nice function to optimize yet. And to obtain a nice function to optimize, then we use the logical connective soft constraint functions from Ye et al.'s paper, Synthesizing Open Worlds with Constraints Using Locally Annealed Reversible Jump MCMC. So now that we have obtained our scene layout using the optimization of this function, we can generate the corresponding text. And we do that with a pretty simple natural language generation pipeline, which in a certain order determines first what should be in the text, then builds sentences from that, aggregates them so similar sentences are combined together. For example, for the 2 sacks of flour, it makes more sense to contain them in one sentence. Finally, chooses the right words and generates referring expressions. That means so that every object in the scene is uniquely recognizable within the text, which is not a problem for such simple graphs, but will be a problem for more complex graphs. While state-of-the-art methods for graph-to-text generation use machine learning, this is a good way to obtain a reasonably good textual description in a non-data-driven way. Finally, the description we receive for this example scene would be: the scene consists of a mill next to a road and a pine tree. The mill consists of 2 sacks of flour to the right of the windmill building. Let's look at some more complex scenes and evaluate how well the descriptions are. The primary way to evaluate scene layouts and texts is usually by user studies, and that's why we performed a small pilot user study with just 29 participants, where in 2 sessions we first asked them to evaluate the scene layouts and provide their own textual descriptions for scenes. And then in the second session we asked them to observe a number of scene layouts with each a machine description and a user description, so they could compare and for both of them rate which one they found more accurate. So let's take a look at an example scene layout with some texts. As you can see, it's the scene layout from the title slides, and the machine description on the right is quite long for it. It enumerates all the objects, all the clusters in the scene, tells you that there are some market stands there next to an intersection and a small forest, basically. If we look at the both 2 human descriptions, they are a lot shorter, and some of them are really good, like the first one. There's a dirt path with a crossroads. Next to it, there's a small forest with thicket. The path has a place with 2 meal counters and 1 plants counter, which is a pretty accurate description of the scene. It's lacking some of the details, but honestly, it's a good summary. If you look at some other user descriptions, though, they are not as good. For example, a mostly empty field with a few trees and 2 streets that intersect. On one street there's a small square on one road with 2 tables and 3 pole posts. This description does not make the abstraction that those tables with stuff could be market stands, and it lacks very much detail for describing the scene. And so maybe it does not come completely surprising that machine descriptions can perform better than some user descriptions, if not all, but not all of them. So this is reflected actually in our results, where surprisingly enough, if we ask the participants to rate for each text that this text describes the scene accurately on a Likert scale, whether they agree or disagree, it turns out on average the machine description even outperformed the user descriptions. However, as you could see, there are some poor quality user descriptions, and if we filter those poor quality user descriptions out by basically just allowing the best user descriptions to be compared to machine descriptions, then suddenly the image is different and the machine descriptions are of course worse than user descriptions. I guess this is to be expected, but let's have a quicker look what is the main problem with the user descriptions, why on average the machine description could outperform them. Well, that is basically, as we discovered, because they were low effort and short. And as you can see here, we have plotted on one axis the word count and on the other the average participant rating of description with a blue dot for each user description and an orange cross for each machine description. And you can see there's a correlation between word count and rating for the user descriptions. And if we filter out all those short, low effort user descriptions and the long machine descriptions, so we get on average the same description length, it turns out that on average the user descriptions perform better, which is to be expected. But actually, if you look at this area in the middle, the difference is not as stark as you would expect, and the machine descriptions are only slightly worse than user descriptions. Our system has failure cases as well, which are usually caused by problems in the scene layout generation. Here I have an example where it's immediately obvious to you that there's way too many lanterns, so the graph grammar definitions could be improved. And in addition, you can see that in the first sentence of the machine description, it says the scenes consist of 4 roads reaching at an intersection. And if you look at the scene, this is clearly not what happens. So there's some disparity here between the scene layout that was generated and the scene relationship graph that planned the scene. The human provided descriptions you can see on the left here are not affected by this problem, since they are not informed by the scene relationship graph. So let's discuss these results. As you see, generating scenes and descriptions at the same time is feasible in our proof of concept. Our texts are actually quite accurate as rated by users, but everyone can, I think, tell that they are machine generated because they are just an uninspired list of things that are in the scene and how they relate to each other. The scenes that are generated are plausible with some flaws. I did not show you the material from the user study for that due to time constraint, but you gotta believe me that they fared okay in the ratings. However, there are some issues with pathway and clipping, which could be resolved by fine-tuning the Markov chain Monte Carlo optimization step. And what's actually really nice about our graph grammar approach to generating scene relationship graphs is that our output is user controllable if you know how to define graph grammar rules, which can be learned in a couple of hours, I think. So this is actually quite a nice feature compared to machine learning methods, which would rely on large data sets, which we would have to collect first. And here you just start a graph grammar, annotate some 3D models with some collision data and textual description data, and you're good to go. In general, we would love to see more research on generating scene and descriptions at the same time, but more also on generating descriptions for 3D scenes. Because I really believe that this is key to understanding the text 3D scenes embeddings that relate those things to another, and actually will help us in the future to generate 3D scenes from text as well. So this is pretty much a call for future research, which we hope to participate in. Of course, you can find all the details about the method, the user study, and further examples produced by our system in the short paper and its supplementary material. Now on this slide you can see some of the key literature, and with this I'd like to thank you for your attention.